Alright, the topic today is conservation of momentum. I am Imani Wiley, and this is James Lyles. Together, we will be presenting this topic. So, what you have to understand in conservation of momentum is first what it is to be conserved. It means that what our momentum needs to be is constant or unchanging. Now, it would be only during collisions that we really allow the laws of conservation of momentum to apply. So, what does this mean, essentially? It means that your momentum before your collision needs to be the same thing as your momentum after your collision. Now, the individual objects in the system may change their momentum, but the net momentum in the entire system will be the same. Also, something to keep in mind is that if momentum is conserved, then the energy is conserved. That means the net kinetic energy in the system will still be the same. Now, when looking at what this means as an equation, if we know momentum equals mv, momentum being p, and mv being mass and velocity, of course, then the law of conservation of momentum is simply saying that your p initial has to equal your p final. What you have at the start needs to be what you have in the finish. Now, alright, so what we have here are elastic collisions, and we're going to use several different cases. We're going to keep it one-dimensional simply because we don't want to complicate things with the vectors in the x and y and z direction if we go 3D or 2D. So we're going to keep it one-dimensional. Now, in this case, we're going to have M1 and M2 equal each other, things of the same mass. And M2 will be static, not moving, while our M1 will be moving at 5 meters per second. So what happens when an object that is moving collides with an object that is not moving and they are of the same mass? Well, we see what it looks like before the collision, and we see that our initial momentum, which is just the sum of both of their momentums, is 5 kilogram meters per second. Now, if you go ahead and look at what happens after the collision, there's been a change in both systems' momentums. The velocity of M1 became 0, while the velocity of M2 became 5 meters per second. Now, despite the fact that both of them now have a new momentum, the overall net momentum has not changed. So what we see here is a simulation. We're going to go ahead and show you this in actual practice. Now, we're using the exact same scenario that we just showed in the previous example. We're going to have masses be exactly the same, while mass 2 is completely static and mass 1 is moving at 5 meters per second. Let's look at the end result. They give us the momentum right here, 5 in mass 1 and 0 in mass 2. So the total momentum is 5. Now, let's watch what happens during the simulation. So we see that mass 1 now has become completely static and transferred all of its momentum onto mass 2. So that even though our momentums have essentially switched in each object, the total momentum is still 5 kilogram meters per second.
Okay, so as we had in the example on the screen, we have two equal masses here. One's going to be static at 0, and this one is going to come in moving, and watch this, you'll see it. And as I push mass 1 into mass 2, which is at 0, you'll see the momentum is changed from one mass to the other, forcing one to go down the track as one stays still right here in the middle.
Alright, so now we're going to deal with something a little bit different. Now, what happens when they're not the exact same mass? Once again, for the sake of simplicity, we made it by a multiplying factor here. Now, M1 is moving to a static 2M1. In other words, the object that is static will be twice the mass of the mass that is colliding with it. So, for the sake of simplicity, we're going to go ahead and make M1 1 kilogram and M2 2 kilograms. So M1 is half of M2, V1 is 5 meters per second, and V2 is 0 meters per second, which means the momentum in the second object is 0. So our total momentum would once again be 5 kilogram meters per second. Now, if you look at what happens after the collision, this time the velocity is distributed between the two when they collide. Now, you see that M1 walks away with a negative velocity headed in the opposite direction, and M2 moves forward in a positive direction based on the collision. Now, what you'll see is M2 has a higher velocity because M1 was headed to it with more. There was not much to bounce back from for M1 because the object was static. Now, when you take these momentums and calculate them, the final momentum is going to be M1 V1 plus M2 V2. So when you go ahead and do that, you get negative 1.6 kilogram meters per second plus 6.67 kilogram meters per second, which gets you right back to 5 kilogram meters per second. So once again, the system shows momentum will always be conserved in elastic collisions. Now, once again, we'll show you through the simulation, because here it takes out all the forces of friction, sends a very specific, definite velocity, all the things that we can't do in real life. So now you'll see what happens when the mass is double when it's hitting a static object. So as you see right here, the current momentum is 5 kilogram meters per second total. Now, when object 1 hits object 2, they both move in opposite directions, but the total momentum will still be conserved. As you can see, the momentum becomes negative 1.67 for object 1, and object 2 is 6.67. So now they both have completely different numbers than they had before, but when you add them together, the net momentum is still 5 kilogram meters per second. So momentum is conserved.
You go.
All right. So once again, we want to get the idea that the net momentum is conserved. So what we're going to do is take a visual example right here, that even though the objects themselves change position, speed, etc., the net of what is happening will always be what is happening in collisions. Now, take for example 2 static balls and 1 ball moving. 1 ball will always be moving while 2 will always be static. Now, this is exactly what I'm talking about. Watch here as the ball moves. 1 ball moving, 2 balls static. 1 ball moving, 2 balls static. Even though the balls themselves switch positions on what is doing what, momentum is always conserved. All right, now hopefully this is becoming a bit clearer. We're just going to do a few more examples and then that'll be it. So now we're going to look at 2 objects colliding with each other in opposite directions. An actual, what we think of as an ideal collision. 2 objects moving at each other and crashing. So what we have here in this case, we're going to keep the masses the same, M1 equals M2, and simply so you can see the numerical values, we're going to make M equal 1 kilogram. So the velocity is 5 meters for the first object, V1, and for the second object, it's going to be negative 5 meters per second. Now the initial momentum in this scenario is 0 kilogram meters per second. Now what's important to understand is both of these objects are in motion, so even though it's 0 net momentum, these objects aren't going to stop, is the thing. Now, when you look at what happens after the collision, you see that they've essentially switched velocities. M1 now has a velocity of negative 5 meters per second, while V1 has one of positive 5 meters per second. They're now moving in the opposite directions that they previously were. So even though they are still moving, the net momentum is 0, and the overall momentum is conserved within the system.
Here for the visual, we'll have 2 masses of the same weight, and they will be traveling towards each other with the same momentum and velocity. And as they come towards each other and they collide, momentum will be conserved. And so look, let me show y'all.
All right, so in this final example here, we're going to have M1 moving to 2M1 and in the opposite direction. So in other words, we're going to have 2 masses collide with each other at the same speed, but one mass is massively larger than the other. So what happens when those 2 collide? So once again, for the sake of simplicity, we're going to have M1 be 1 kilogram and M2 be 2 kilograms. M1 is moving at a speed of 5 meters per second, while M2 is moving at negative 5 meters per second. So here's the image we have before our collision. At this point, when you take their momentums, a momentum of 5 kilogram meters per second and negative 10 kilogram meters per second, the initial momentum is negative 5 kilogram meters per second. Now, after the collision, they've completely changed to different speeds, and even though their masses are the same. So now they both have completely different momentums. As we see here, the new velocity for M1 is 8.33 meters per second, negative 8.33 meters per second. And for the M2, the new velocity is 1.67 meters per second. So now when we calculate our final momentum, we'll see the momentum was conserved even though each object's individual momentum has changed. So when you look for the final, you do M1 V1 plus M2 V2, or however many objects are in the system. So when you add that negative 8.33 kilogram meters per second to your 3.33 kilogram meters per second, you get the same negative 5 kilogram meters per second. All right, now to give you guys an accurate understanding of what we mean, we're gonna have you look at this simulation. So we've got a mass of 1 kilograms moving at 5 meters per second towards an object that is moving in the opposite direction that is twice as massive. We've kept it one-dimensional so you don't have to keep track of the many vectors that'll be going on if we were to make it 2 or 3. So as you see here, the overall net momentum is clearly negative 5 kilogram meters per second from adding the 5 and the negative 10 of your two objects. Now watch what happens post-collision. Alright, that was a little fast because these objects were very close to each other, but as you can see in the numbers here, their velocities have become completely different values. Their momentums have become completely different values. But regardless, when you add their net momentum, it still is the negative 5 kilogram meters per second. Momentum is always conserved. Alright, so in conclusion, the thing to take away from the conservation of momentum in elastic collisions is that your momentum at the beginning will always be equal to your momentum at the end. Another thing to take away could be the idea that as long as energy is conserved, momentum will also be conserved. All of that is seen from the several following examples. Alright, so that would be Imani Wiley, James Lyles, signing off. See you next week. Conservation of energy.